This is example 3.13 on page 104. The time t between breakdowns of a major equipment in an oil platform is defined by a log normal distribution with a median of 6 months and a coefficient of variation of 0.3. In order to ensure a 95% probability that the equipment will be operational at any time, the question is asking for the interval between inspections and repairs. So we start with the information that's given. We have the median equal to 6 months. So we have x sub m is equal to 6. And we have the coefficient of variation equal to 0.3. You recall the definition of the coefficient of variation is the standard deviation divided by the mean is 0.3. The coefficient of variation, your textbook makes an approximation. They say that when the coefficient of variation is 0.3 or less, we can make the approximation that the natural log of 1 plus 0.3 is essentially, in this case, 0.3 squared is essentially equal to 0.3 squared. And therefore, we can say, well, zeta, because we take the square root, we're given in the definition zeta squared is equal to this term. And the approximation is giving that squared, so we take the square root of both sides. So essentially saying that zeta is equal to the coefficient of variation, which remember is the symbol is delta x that your textbook uses. So this is the first piece of information that we are going to utilize, given that we have the coefficient of variation equal to 30%. The median, remember the median is defined by, in the log normal distribution, as the median is equal to e raised to the lambda. And since we are given the median, well, we could also solve for lambda, and lambda is equal to the natural log of the median. So therefore, lambda is equal to the natural log of 6. And in this case, we have 1.792. So we have zeta, which was 0.3, and lambda. So we have our parameters for our log normal distribution given to us in the problem statement. Now, whether or not this is a good approximation, I've discussed this in the lecture. When it's close to 0.3, there's some question about it, but when we get smaller than that, I would agree that it is a pretty good approximation, as I stated before. But we're going to go with, we're going to be consistent with what the textbook does, and you're safe to make this assumption if you choose to do so rather than crank it out. So what we want to find is the 95% probability that the equipment will be operational. So what we're asking in terms of probability is the probability that the time greater than some value t sub 0, and this is what we're after, this value t sub 0 is going to be 95%. And this, since we're using the time greater than, what we like to do instead is the complement of that. So we do the time, the complement of this. So we go 1 minus the probability that the time will be less than or equal to some value t0. And we want to make this 95%. This is our 95% probability. So less than, greater than t sub 0, we want 95% probability, but less than, in order to make this, when we switch this around, then what we're saying is that the probability in this case will be less than 5%. Right, so what we're going to do is flip this around and say that we'll take the CDF function of the natural log of t0 minus lambda, which is 1.792, divided by zeta. 0.3. We're going to set this equal to 0.05. Okay, so we're doing the same thing here. So this is the same thing as 95%, or 1 minus 5% gives us 95%. So that's all we've done here. So we have ultimately the natural log of t0 minus 1.792 is equal to, when we take the inverse CDF function of both sides, we have 0.3 times the inverse CDF function of 0.05. Now remember, we're taking, this is the probability that's in here, we are taking the, we're trying to find the value, but because our probabilities start at 50%, we can't take this. But remember from our definition, this is the same thing as the negative CDF function of the complement. So this is also equal to 0.3 times the negative CDF function of 0.95. So we end up with 0.3 times a minus 1.65 when we go and look this up on the tables, which is equal to a negative 0.495. Therefore, when we add 1.729 to that, bring that over from here, we end up with the natural log of t0 is equal to 1.297. Take the exponential of both sides, we end up with t0 is equal to e raised to the 1.297, which is equal to 3.66, in this case months. In the next part, it says if the equipment is in an operational condition at the time it is scheduled for regular maintenance and inspection, the probability that it will remain in operational without breakdowns for another 2 months would be. So we're asking a conditional probability here. We're saying that if the equipment is operational at the time it is scheduled for regular maintenance, which is 3.66 from the previous part, then the probability that it will remain operational without breakdowns for another 2 months. So 3.66, another 2 months would be 5.66. So in probability terms, what they're asking for here is the probability that t is greater than 5.66 conditioned on the probability that t is greater than 3.66. So remember, from conditional probability, the definition is the probability that the time is greater than 5.66. And we're doing an intersection, so intersection symbol, probability of time is greater than 3.66. And we divide that by what we're conditioning on, the probability that the time is greater than 3.66. So let's look at the numerator. The numerator is simply the probability that the time is greater than 5.66 intersecting with the probability that the time is greater than 3.66. So the only way this being an intersection here is for all times greater than 5.66. So this is really just simply the probability that time is greater than 5.66, and we're dividing by the probability that time is greater than 3.66. So the probability that the time is greater than 3.66, well, we figured that out from the first part where that was imposed on us. This is 95%, because this is what we were asked to determine in the beginning, that is that time, but since they gave us the probability, they forced us into a 95%. So this is going to be the probability that time is greater than 5.66 divided by 0.95. And the probability that the time is greater than 5.66 is equal to, it's the same thing as if it's less than 5.66, 1 minus if it's less than 5.66, so we take the complement of that, which is the CDF function. And again, we're going to log normal distribution, so we need to take the natural log of 5.66 minus 1.792 divided by 0.3, that whole thing over 0.95, which is 1 minus the CDF function of a negative value, 0.195 over 0.95. Now remember, when we have the CDF function of a negative, this is simply going to be 1 minus the positive value of the CDF. So 0.195. It's the same thing. Right? A negative CDF, because of our tables, we don't have negative values, so we have to do a positive value, and it's the same thing. When we take the positive value, it's 1 minus the positive value. So it's that symmetry over 0.95, and when we crank all this out, we find that it is 0.61.